let's change topics now and look at something known as linear approximation. Linear approximations are used a lot, both linear and nonlinear, and we will get into much more detail with this in Calculus 2 and again in Calculus 3. But for now, we're going to start with an introduction to what linear approximations are all about. Now, in terms of the learning objectives for the next several videos, we want to be able to approximate either a polynomial or a transcendental function using a linear approximation. So let's just jump into it and take a look at just what this stuff means. First of all, consider the function negative of x minus 2 quantity squared plus 3, which is this guy right here. If I zoom in enough, I'm going to pick a spot like where x equals 1. Pick a spot right here. If I zoom into this graph right there enough, it's going to look like a straight line. Let's just go ahead and do that quickly in Maple. I'm going to plot, let's see, a negative of x minus 2 squared plus 3. And I'm going to go ahead and let x go from negative 1 to 5, and y go from negative 1 to, I don't know, 3 or 4 should be enough. Let's do 4. I'm going to set thickness equals 2, just so the line's nice and thick, make it easier for you to see. So this is what the function looks like, the same thing you just saw on the screen. So when x equals 1, I'm right in here, close to 2. So I want to zoom in on this right here. So to zoom in on it, go click on the function and come over here. And now I can zoom way in on this thing. And I need to move it a little bit, so I'm going to grab the hand tool, scoot it around. See, here's x equals 1, y equals about 2. Come back in and zoom in yet some more. And I'm going to adjust it again just a little bit, move it over. And you can see that as I zoom in more and more and more, that this thing is starting to look straighter and straighter and straighter. I mean, it's looking pretty darn straight right there. So the idea that I could take values near x equals 1, y equals 2, and approximate values near this on the y-axis with some type of linear function should seem extremely reasonable. Because, like I said, I'm going to zoom in just a little bit more because I think this is kind of cool. I just keep zooming in on this, and it just starts to look like a straight line. And if I were to start off with this, you probably would have thought this was a straight line. But it's actually a piece of this curve right here. Now, a logical representation in terms of a straight line here would be that of the tangent line. So I should be able to use the actual equation for the tangent line to get estimations of this function near this known point. Now consider this function, which is an absolute value function. If I pick x equals 1, I could do the same sort of a thing using a tangent line, but there's an issue right here and right here. And that issue is, if I take that point, there's an infinite number of tangent lines that goes through that point. And that point it's not a smooth point, that's a cusp. So what this is suggesting right away is that for this tangent line type approximation to actually work, my function must be differentiable at the point that I'm working with. Here, it's not differentiable at these 2 points. It's differentiable every place else, but not at those 2 points. So we can actually use the equation of the tangent line to the curve at the point A, F, and A as a linear approximation of the curve near A, F of A. So if I say A is 1, right here, that's F of A. So I actually have this point that I'm going to be working with, 1, 2, on this graph. So the point here is that I know I have a known point. So if I have the equation of this function, which I actually do have, if I take the derivative, if I find f prime at A, that's going to be the slope of the tangent line at x equals A, in this case 1. So now I know the slope, it's f prime of A. I know a point. That point is a f of a. So I can find the equation of this tangent line, which you've done several times before. I can use the idea that y minus y1 equals the slope times x minus x1, where y1, x1 is a known point. Right there is x1, right there is y1. So what I have is y minus f of a is equal to the slope, which is f prime of a, times x minus x1, but x1 is a. That implies that y, the equation of my tangent line, will be f of a plus f prime of a times x minus a. So anywhere near a f of a, very close on the x-axis here, very close here on the y-axis, I should get a very good approximation. But notice quickly that as I get farther away from a, say I pick a point over here someplace for some value of x, now my linear approximation, which is on the line, is going to be pretty bad. If I come way over here, then this curve comes way down, then my approximation is even worse. So as I start getting away from this known point, my approximation starts getting worse and worse and worse. But near that point, it should be pretty good. Now, obviously, to do any of that, because I have the derivative in there, this requires f prime of a to exist. That's an absolute requirement because right here is f prime of a. I can't have it in there if I don't know what it is. So that's the basic idea. In order to do a linear approximation, all we're going to do is find the equation of the tangent line at a point on the curve and then use values on that tangent line to approximate the curve near the known point. Again, as we get farther and farther away from that known point, my approximation is going to start falling apart on me.